How's it going, ladies and gentlemen? Mr. Johnny here again, going over some chemistry problems, looking at 8.8 strength of covalent bonds. You can do a little math, but not on this first problem. First problem is kind of a toss-up. Hopefully you read and you understand, of the bonds, carbon single bond, this stupid box should be a double bond. And then triple bonds, it says the C single bond is, well, single bond is going to be the longest. Things as they get multiple bonds, the closer they get and the stronger the bond is. So we're talking about single bonds, the longest and the weakest. So which option is that? C, weakest and longest. 38. So using the table of average bond energies below, delta H of the reaction is blank. All right, so you got to remember that when you're having a reaction, what you're doing is you're breaking those bonds, right? You're breaking them and you're making new bonds. So you got to go, well, how much energy does it take to break each of these bonds? And how much energy am I getting out when I'm making these new bonds, right? So that's what we're going to be doing conceptually. So let's take a look at the math, all right? So in the reactant side, looking at things, we have 413 joules, right? That's found right here for each carbon-hydrogen bond, 413. And that triple bond takes 839 kilojoules to break. Now we got an HI bond right here, which is 299, right? So how much energy does it take to break all those bonds in the reactants? Well, we're just going to kind of add them up. And we do that math, and hopefully we get 2,263 to break it. Now we take a look. Well, how much energy do we get out from making all those bonds? Well, I'm going to look at my CI bonds. I got 2 of them, right, at 240 a pop. And how many CH bonds do I have? Well, I got 4 of them at 413 a pop. So how much energy am I getting out of this? Beep, bop, boop, boop. 2,480. So we're putting in this much energy and we're getting out that much. So what's the overall change? Well, just do the math, do the subtraction and get negative 217, right? We're getting out this energy, so that's a negative thing for our delta H, right? So overall change would be negative 217. So you just look at the bonds. How much energy does it take to break those bonds? How much energy do you get out when you make the new bonds? What's the difference? All right, 39, same thing, but different, right? So let's take a look at the reactants, all right? How many CH bonds do we have? We got 2 of them. So it's 2 times 413. All right, well, what about this C triple bond? Well, we got 1 of them at 6,4, no, wrong one, 839. And then we got this HI bond as well, right here. How much energy does it take to break that? 299. So we add all those up, and what do we get? 1964. That's how much energy we got to put in to break all those bonds. So again, this stupid box should be a double bond. So let's take a look at the products. Well, we got CH bonds, right? And we got how many of them? 3. Count them. We got 2 here, and then we got 1 more over there. So we got 3 times 413. And we have a C double bond, C. So that energy is 614. And we got this CI bond right here, which is hiding a little bit. Just right there. CI, 240. So add all those up, and you get the answer, 2093. So we're putting in this much energy, and we're releasing that much energy. So what's the overall change? Negative 129, right, which would be choice B. 40. From the information given below, calculate the heat of combustion of methane, CH4, in kilojoules per mole. Start by writing the balance equation. All right, cool. My favorite reaction, combustion. Methane, that's fun to blow up. So you start with CH4, right? Reacted with oxygen. And what do you get from combustion? Well, you get CO2 and water, right? And now you got to balance it. Well, I know I got 4 hydrogens here. I only got 2 there. So how can I balance the hydrogens? Well, let me put a 2 in front of this H2O. So now I got the same amount of hydrogens on both sides. That's happy. I have 1 carbon and 1 carbon, so that's happy. But this oxygen, I have 2 here and I have 2 here. So I got a total of 4 oxygens. All right, well, I only got 2 on the reactant side, so I balance out by putting a 2 in front. Awesome. So now I got my balanced equation. And now I can start figuring out this Hess's law bond dissociation energy stuff. So reactants, I got CH bonds. I got 4 of them times 413 for each. Right? I got an oxygen double bond, and you got 2 of them. Right? You got 2 oxygen double bonds you got to break. So it's 2 times 495. Add those up together, and you get 2642. So that's how much energy you're investing to break those bonds. So let's take a look at the products though. We have 4 HO bonds, right? Because of the 2 here and the 2 there, we got 4 of those. So we look up OH, it will be running out of room. Running out of room again. So OH, right? We got 4 times 463. And C double bond O, we got 2 of them because of CO2 looking like this. All right, so 2 times 799. Add those up together, you get 3450. And well, what's the difference? We put in this energy and we got out this energy. So the overall change would be 808 kilojoules per mole. And it's got to be negative because it is being released. It's an exothermic reaction. It gives off heat. All right, cool. And then 41, last but not least, 41. Using the table of average bond energies below, calculate delta H for the reaction is blank kilojoules. Right, same thing, just a different problem. Right, so it's balanced for us. That's nice. We look at the reactants. We got C double bond O. That's going to be just one of them, so it's 799. And we got 2 H bonds. So HH bond is going to be 2 times 436. Add those up together, and you get 1944. All right, we look at the products. All right, well, there's definitely some CH bonds going on, right? How many? There's 3 right there. So 3 times, where is it? 413. All right, well, what other bonds do we got going on? We got a CO bond, right? So I looked that up. That's 358. What else do we got? We got an OH bond as well. So I looked that up, 463. Add those up together, I get 2060. Right, so we put in this much and we got out that much energy. So what's the overall change? 116 kilojoules is being released. So the delta H would be negative 116, which would be choice E. Hope you found that helpful. If not, ask me questions in class, because that's where I'll be seeing you. See you guys in class.